Good morning, everyone. We were looking at calculating the effects of nonlinearity. And we saw that there is a step-by-step way of doing this. So the way to do it is, if you have a nonlinear element in a circuit, I'll just show one or maybe two of them. Some two different nonlinear elements. They don't have to be two terminal elements, but this of course works with any number of elements. And I'll assume that both are represented as the IV characteristics are represented as currents as a function of voltages, but it could be the other way around also. Okay, then you just have to use voltage sources instead of current sources. Okay, so the first step is, and let me show one input. Again, you can have multiple inputs, that's not an issue. In the first step, you take the linearized equivalent at the operating point. So you replace this with their linear equivalents. Again, in general, it can be any number of terminals in the element. You just need to know their characteristics. And these conductances could be G1 and G2. Okay. And in this, you do the circuit analysis. And you find and I'm using this subscript. Additional script to indicate the step, basically the order of the output that you are calculating. So this will give you V1 of 1, V2 of 1. This is the conventional linear circuit analysis. Okay. And from this, for each element, this is basically the first step. And in the next step, you calculate the nonlinear effects because of these first order outputs. Okay. So in the second step, you calculate the second order nonlinear currents that result from the first order voltages. I say voltages if the nonlinearity is described the other way around, that is voltage is a function of current, you do it the other way around also. Okay. So that means that, so let's say we have the element 1 in which I1 is f of V1, which I'll just write as, let's say, hello, was there a question? Is there a question? Are you able to hear me?
Yes, sir.
Okay. So I1 is f of V1, which could be represented as, let's say, A0 plus A1 V1 plus A2 V1 square plus A3 V1 cube. I will stop at that point. But of course, there could be more terms also. So for the operating point and first order, you would have used these two. So in the second step, basically, you use this one. Okay. So essentially, you represent this as an additional parallel current source, and with V1 substituted by just the first order stuff that you calculated in the first step. Okay. Right. So essentially, you will have an additional source. I mean, if I use exactly the same point, which is some current A0, and then a conductance A1, this is the for the operating point, and this is for the first order. And for the second order, I will use this current as the input. Okay. So in the previous lecture, we saw an example with sinusoidal sources, in which case you will have, if the V1 of 1 is a sinusoid, then this will have a DC term and a sinusoid at double the frequency. But in general, it can be any waveform. Okay. Most commonly, we do it with sinusoids. And to do it for the second element also. So the second element, if V2 with I2 and V2, I2 would be represented as G of V2, which is, let's say, B0 plus B1 V2 plus V2 V2 square, and so on. Okay. So this would get represented as the operating point B0 plus a conductance B2. This is for the first order. And for the second order, you current source as this input, right, which is V2 of 1 square. Okay. So you do circuit analysis. So this still the important thing is now you set the input to 0. Okay. And essentially, wherever you had the first element, you would have the operating point. Earlier, I didn't show it explicitly. I will show the operating point A0, a conductance A, additional current source, A2 V square, and exactly the same thing for whatever other elements you have, right? And then you still do, this is linearized circuit at the operating point. Sorry, I should not have put the operating point in this. These fixed sources will go away in the incremental circuit, right? This is the linearized circuit at the operating point with additional current source inputs. Okay. So now you do the circuit analysis and you calculate all the voltages and currents. I'm showing only the voltages and currents on these elements, but whatever you get at these, I'll call it V1 of 2, and this is V2 of 2. Okay. Is this fine? Any questions so far? So essentially the second step consists of whatever comes out of the second order nonlinearity, those are the sources. The input source, whatever you think of as the signal input to your circuit, that is 0. And then you do the circuit analysis. Okay. And then you will get these second order solutions, V1 of 2 and V2 of 2. Right. So this method, this is called the perturbation method or the current injection method. Okay. So essentially the current injection method, it is called that because you have these nonlinear terms represented as additional currents. Perturbation is essentially you have your original solution, like in the analogy I gave, you have your original simple interest solution, and to calculate the compound interest, you add these additional perturbations to it. Okay. So in each step, you assume whatever you have calculated until the previous step is the actual voltage, right? Now, next is, of course, third order terms, and this, of course, quickly blows up because up to this point, you have in the first step, the solutions are basically for all the node voltages, you get some solution. Of course, you get the branch currents also. Now, the solutions from the second step, okay, and the total solution so far would be, right? We have some solution from the first step and the second step. Now, the next step, you calculate the third order terms. So this is the second order calculation. So where do you get third order from? For instance, again, if you look at the element with V1, basically the element D1, you have I1 to be A0 plus A1V plus A2V square plus A3V cube and so on. So now you can see that, sorry, this is V1, right? V1 square, V2, V1 cube and so on. So the third order terms, you would get them from, you have A2. So first of all, so far we have the first and the second order terms like being squared like this. And then you have A3 Okay. So now what is the third order term? Basically, whatever gives you a total order, that is 3. Okay. So from this, the third order terms are, so here we would get, this is the second order term. We have already taken care of this. This is the third order, first order getting multiplied by second order. Okay. And you also get, this is a fourth order term. So we only use the third order terms. Once you know the scheme, you don't even worry about the other terms. You just take this 2v1, v2 term. Okay. And in the other one, I won't write out all the terms, but you can see which is the third order term in this. There is only one that gives you third order term. All the other terms will give you higher orders, right? Because you have v1 of 1 cube. This is third order. And all the other terms like 3 times v1 square times v2, this is fourth order and so on. Okay. You have higher order terms only here. Okay. So we only take this one and this one. So in this case, the additional current source, this will be times 2 plus A3 times V1 cube. Okay. So everything is exactly the same as this one, except now the current sources you consider are different. Okay. So I'll just copy the same picture, except that now okay. And these, as I already mentioned, this will be A2 times 2V1 first order times V2 second order plus A3 V1 first order cube. And this will be 2 2V2 first order times V2. Again, I think I made a mistake here. All this should be V1. V2 second order plus A V3 V2 first order cube. Okay. This is the third step. So it can be tedious to calculate many steps, but hopefully the technique itself is clear, right? Of course, by hand calculation, typically we don't go beyond these 3 steps. You calculate in terms of harmonics, you can calculate the second and third harmonic like this. Okay. So this is the method of current injection or method of perturbation for calculating it. And this is a way of accurately calculating it, right? Not just specifying some spring limit and saying that you cannot apply signal beyond that. Usually what happens is, as you increase the amplitude of the signal, the harmonic strength increases, and you have to limit your input signal to an amplitude that gives you the specified distortion. Maybe the distortion has to be, let's say, 1% of the fundamental or 0.01%. There'll be some limit depending on. So that is where you have to limit it. Now, for that, you have to be able to calculate the amount of the magnitude of nonlinear products, and you can do it like this. Any questions on this? This method of current injection? So it's a systematic procedure, but of course it can be tedious because as the order of nonlinearity grows, the number of terms you have to take into account grows as well. But you can certainly take it to any order. I mean, that is very much possible. Okay. So we have acquired now by now a lot of background knowledge on IC design, what components you have, how they behave, peculiarities of IC design, these large process variations and so on. And we also know how to calculate the effects of random mismatch and random noise, right? And so from now on, we can go on to build the circuits that we really want. With all this background, we can start with circuits that we want to build on an IC. We'll do that. Before that, there's a little bit of more background information, and we can start a new topic in a later class, right? So one just a miscellaneous point, which I did not mention earlier, right? So this is about noise. We were discussing this noise scaling or impedance scaling. And this impedance scaling, this works for both thermal and flicker noise. Okay, that is if you scale up a circuit by a factor of 2, that is we are saying 2 parallel circuits, both thermal and thermal and flicker noise spectral densities